Hello students, welcome to this lecture on different kinds of the logic circuits. So up till now what we had seen is a regular CMOS family or the regular CMOS designs, and then we had seen the pseudo NMOS CMOS logic. So in this particular lecture we will look into two different logic families. One is the Ganged the CMOS logic family, and another one is the dynamic logic families. So let's begin this lecture just to with an understanding of the pseudo NMOS circuit, and then I think we will dive into the Ganged CMOS logic family. So let me quickly draw the pseudo NMOS inverter. So the pseudo NMOS inverter, as we know, that the PMOS should always be on. So that has to be there. So it is always connected to the ground. And the NMOS is connected to the input. So the gate of the NMOS transistor will be connected to the V input. And then based on this particular V input value, we will get the output. So I will also draw the rail VDD, and then of course this is the ground, and then this is my output. So this is this is how the pseudo NMOS inverter the schematic looks like, pseudo NMOS. And what we need is to get a current while it is actually the output is going down. To get a current of I, we are having a size of 2/3 and then 4/3. And the reason for doing this is because 2/3 will always because this PMOS is always on. So this 2/3 width is going to give me a current of I/3 here, and that will always be a current of I/3 here, even when the input is 1 here, so that I'll get the NMOS to be on and the output is going to be continue to discharge with a current of 4I/3. So the NMOS has a current of 4I/3, and the capacitor will be discharging with a current of I. So 4I/3 minus of I/3 will give me a current of I from the capacitor side. So let me draw the capacitor also so that it becomes easier for one to see. Right, so we need a size of 2/3 and 4/3 so that the capacitor discharges with a current of I, and then this I/3 is the PMOS current which will be driving the capacitor to charge, and 4I/3 is the NMOS current, and thereby the capacitor has 4I/3 minus of I/3, that becomes I. So this is one kind of the logic family. So now let's use the same size and draw the regular inverter, right? So if I use the same size and draw the regular inverter, note that the regular inverter, the input is connected to both PMOS and NMOS. So I will use this, and this is my input now. So I'm going to write this input as A input. And the size of this particular the regular inverter is same as that of the pseudo NMOS one which I've drawn. So 4/3. Now because the PMOS is not continuously on, it depends on whether A is 0. If A is 1, the PMOS will be off and NMOS will be on, and when A is equal to 1, the NMOS will be on and PMOS will be off, or A is equal to 0, PMOS will be on and NMOS will be off. So my driving current here, so let me use the same color. So my driving current here will be I/3 on the pull up side, and then it will be in fact 4I/3 on the pull down side, right? The reason is simple. Even if I have a capacitor here connected, or whatever the parasitic capacitance, this capacitance will have to be driven by this 4I/3 current, right? Because the PMOS will be off when A is equal to 1, the NMOS will be on and then the PMOS will be off. So there is actually no channel for the capacitor to get charged continuously, right? So this is off, and thereby this NMOS will be on and then capacitor will get discharged to 4I/3. Okay, now with this particular understanding of 2I/3 and 4I/3, so let me draw one more circuit. Basically the circuit will be nothing but two sets of inverters. So let me draw it here, although in a small way. So I have one inverter, and this is my one input, and I'm connecting one more inverter. Of course, this is the VDD rail and this is the VDD rail. The same rail goes there. And of course, this is the ground rail, the same ground rail. And I will have one more input, right? This input is called as B input. So there are two inverters. And now I'm going to connect the outputs of these two inverters. So I'm going to connect the output of these two inverters together and call this as the final output. Okay, and now I'm going to size this up, right? Similar to the pseudo NMOS, similar to whatever the inverter I have drawn here, that is 2 by 3, 2 by 3 on the PMOS side, and then 4 by 3 on the NMOS side. Okay, so these sizes are actually derived from the pseudo NMOS inverter. And let's say that, and I'm going to pick one such combination when, let's say, A is equal to 0. Okay, so A is equal to 0 and B is equal to 1. So there are two inputs to this particular circuit, whatever that circuit is. It's no longer an inverter because there are two inputs. So it should be an AND gate or an AND gate or an OR gate or a NOR gate or whatever, XOR gates and so on. So if I pick A is equal to 0 and B is equal to 1 as one such combination, so A is equal to 0, that means A is equal to 0 says that this one is on, this particular PMOS is on, this particular NMOS is off. So I'm actually writing it out. And B is equal to 1 represents that this NMOS is on and this PMOS is off. So now I have two of the transistors out of 4 transistors which are on, right? And in a way that it says that the PMOS transistor is on this A side, and on the B side the NMOS transistor is on. All right, and the outputs are connected here by this kind of a red wire here, right? So what it means is I will have a current of I by 3. So I'm going to write this, the current of I by 3, the PMOS of 2 by 3 width is going to give me a current of I by 3, right? And here B is equal to 1 will give me a current of 4 by 3. So because the width is 4 by 3, so this one will give me a current of 4I by 3. Right, so when A is equal to 0 and B is equal to 1, I have now both the pull up and as well as the pull down circuit to be on with the currents of I by 3 and 4I by 3, and thereby the capacitors which are now connected at the output, whatever the capacitors will be, it will basically be the parasitic capacitors of all these 4 transistors will be seen at the at the output node. So this particular capacitor will be discharging at a current of I. All right, hope this is clear to everyone. So I have now a current of I that will be discharging, right? So this ganging up of regular inverters, ganging of this particular inverter and then this particular inverter, ganging in the sense the combining these two regular inverters and then forming a particular circuit is called as the Ganged CMOS family, right? And then the other version is we are using the sizes that of the pseudo NMOS, because I finally want the current of I from the capacitor side, right? So what it also implies is 2 by 3 and then 4 by 3 here when A is equal to 0 and B is equal to 1 is likely to give me a final output of Y is equal to 0, because the NMOS current drive or the current strength is better than that of the PMOS, and thereby I will get finally this capacitor will discharge to 0, right? So here my output will be 0. And similarly, if I take another combination of A is equal to 1 and B is equal to 0, I will have on the B side, I will have the PMOS transistor to be on, and on the A side, I will have the NMOS transistor to be on. The A side NMOS transistor has a better current strength than that of the B side PMOS transistor. and thereby my output voltage will eventually be discharged to 0, and I can say that Y should be 0 here also. Okay, and if A is equal to 1, A is equal to 1 and B is equal to 1, A is equal to 1 and B is equal to 1, I will have both the NMOS transistors to be on and both the PMOS transistors to be off, and the capacitor will be completely discharged to 0, so the output will be 0. So I have now, for 3 input combinations, I will have output as 0. And finally, when A is equal to 0 and B is equal to 0, both the NMOS transistors will be off and PMOS transistors will be on, and thereby the output will be pulled to VDD level or the logic high. So out of the 4 combinations, one combination when A is equal to 0 and B is equal to 0 is giving the output of 1. All the other 3 combinations gives the output of 0, which says that this is a NOR gate. It's a NOR representation using the ganging up of 2 regular inverters with the sizes coming from the pseudo inverters, right? So this particular inverter, what I have drawn here, the 2 inverters connected or tied together, represents the Ganged CMOS NOR gate, or rather I will say that 2 input NOR gate. All right, hope this is clear. So let me quickly go to the next slide. So this is an overview of what I have stated in the previous one. So the size is 2 by 3 and 4 by 3 here, 2 by 3 and 4 by 3 here, and A and B, and I have drawn a truth table here just to summarize all the effect. So if A is equal to 0, B is equal to 0, so A is equal to 0, B is equal to 0, we will have both P1 and P2 to be on. So that's what I've written, P1 here and P2 here to be on, and both the NMOS transistors are off, and Y will be the logic high. The current, the output current, or whatever the capacitance here, or whatever I've written here, it will be charging. So the charging current or the rising current to the VDD level will be nothing but I by 3 coming from the P1 transistors and then I by 3 coming from the P2 transistors. So the capacitor will be charging with a current of 2I by 3. So that's what I've written here. Okay. When it is, let's take an example of 1, the another extreme. So when A and B are 1, so that means that the NMOS transistors are on and PMOS transistors are off. And thereby the capacitor is going to discharge with a current of 4I by 3 on one branch and a 4I by 3 on the other branch. So total current is 8I by 3. Right? So the logic will be anyways be low. Here the logic was high. For the other 2 cases, 0, 1 and 1, 0, we notice that one of the PMOS will be on, the other NMOS will be on. And thereby we will get a total current, the capacitor current of I and I, because it will be nothing but 4I by 3 minus 1I by 3, so it will be nothing but a current of I on the capacitor side, and the output will be low, and that's why it is a 2 input NOR gate. Right, now let's see what is the benefit of the Ganged CMOS over the other set of logic families. Right, so let me take the pseudo NMOS here, the pseudo NOR gate, and if I want to understand the pseudo NOR gate, so let me try to draw that. The pseudo NOR gate, again, I will have a PMOS which is always continuously on, so it is connected to the ground, and it's a NOR gate, so I need a 2 inputs. So I'm going to draw 2 of the transistors on the NMOS side with an input of A and the input of B, and this is my output, right? The size will be nothing but 4 by 3 here and 4 by 3 here, and the size here will be 2 by 3. And this I'm going to call it as the pseudo 2 input NOR gate. All right. What I'm saying is when A and B are 1 here, so I will get I will get the current of 4I by 3 and then 4I by 3 here when both are 1. And in this particular Ganged CMOS, I will get a current of, when A and B are 1, I will get a current of 4I by 3 and 4I by 3. But the point to be noted here is, when A and B are 1 in this Ganged CMOS, the PMOS transistors are off. Alright, so the PMOS transistors are off. That means that the current, the transient current will be 4I by 3 and 4I by 3, right? But after Y reaches a 0, there won't be any other current. There won't be any DC current or a steady state current that will be flowing to the ground, right? Once the Y reaches the value of 0, it will be the current will be 0, right, in the Ganged CMOS, because both the PMOS transistors are off. Here in the pseudo NMOS NOR gate, when A and B are 1, I'll get a current here, right? So Y is likely to reach to a value of 0. But even after reaching 0, there is a continuous current of I by 3 which will be charging the capacitor, right? So there is a current that will be flowing because this PMOS is on, and then thereby the capacitor is going to charge, right? The moment it charges, it has a delta Q charge, it has to be discharged back by this NMOS transistor so that the output stays at 0. So what it implies is there is always a current that will be flowing from the VDD to the ground, always, even after Y reaches a steady state output. So there will be a non-zero current. So I'm going to write it as a non-zero current that will be flowing from VDD to the ground, and thereby I will get some static power dissipation always in the pseudo NMOS NOR gates. So the Ganged CMOS has this particular advantage that there is no static power dissipation, similar to that of our regular inverter. Even on our regular inverter, there is no static power dissipation because the NMOS, if the NMOS is on, then the PMOS side will be off, especially for the 2-input NOR gates. Right? Hope you have understood that. The other advantage in the Ganged CMOS NOR gate, no power dissipation when A and B are 1. So that's what I have explained now. The other one is this particular point when A is equal to 0 and B is equal to 0. A is equal to 0, B is equal to 0. I will have both this PMOS transistors to be on and MOS to be off. Now the pseudo NOR passes if I consider the pseudo NOR. When A and B are 0, the pseudo NOR passes a current of I by 3, right? So it only passes a current of I by 3, lower than the Ganged NOR, which passes a current of 2I by 3. So that's what I have explained here. It passes a current of 2I by 3. When I compare that with that of the pseudo NMOS, it passes a current of I by 3 here, right? So for the rising output, when the output wants to go to 0, the Ganged CMOS structure is likely to have a higher current of 2I by 3, and thereby the delay or the performance will be better. So the delay will be less and then the performance will be better, right? Hence the delay is less. That's what I have stated here. So those are the two advantages. One is the static power dissipation will not be there in the Ganged CMOS, and the other, another advantage is for the rising output, it is much faster. So let's take a look at the the logical efforts here. The logical efforts for the inputs, again, because it is tied to both PMOS and NMOS side, I will get the capacitance from the PMOS as well as from the NMOS. So 2 by 3 plus 4 by 3 will be the total capacitance. And then especially for the rising output sees a current of 2I by 3. So that means my benchmark inverter should be of size 4 by 3 and 2 by 3. So 4 by 3 on the PMOS side and 2 by 3 on the NMOS side, so that I'll get a current of 2I by 3 on the PMOS side and 2I by 3 on the NMOS side, right? This will be the benchmark inverter. So I'm going to write it as the benchmark. All right. So the logical effort will be nothing but, the input capacitance seen on the benchmark inverter, which will be 4 by 3 plus 2 by 3. And the logical effort, or rather, the input capacitance seen by this particular Ganged CMOS will be nothing but 2 by 3 and 4 by 3 on the input A side or B side. Right. So overall, the logical effort is actually 1. Right. For the rising output, the logical effort is 1 for a 2-input NOR gate. So it is very beneficial, right, compared to that of the regular inverter. Right. And then the logical effort for the going down right? For the going down one, we will take the worst case where one of them is on and the other one is off. What I mean is when A is equal to 1 or B is equal to, and B is equal to 0, or A is equal to 0 and B is equal to 1. So I will have a current of I and I here. So my benchmark inverter in this particular case will be nothing but, because it is giving a current of I will have a 2:1 inverter. So my input capacitance of the 2:1 benchmark inverter will be nothing but 2 plus 1, which will be 3. And here the input capacitance is nothing but the same, 2 by 3 plus 4 by 3, which will be which will give me 6 by 3, that is nothing but 2, and then divided by 3 coming from the denominator side. So the overall logical effort for going down signal will be nothing but 2 by 3. All right. So I have now the logical effort for going down is 2 by 3 and logical effort for going up is actually 1. So my average is nothing but 5 by 6, much better than that of the regular CMOS structure to input NOR gates. Right? Hope this is clear. Right. So that is one set of logic family, the Ganged CMOS, and it is kind of very applicable to the to that of the NOR gates, and it is implemented only for the NOR gates circuits. The another very useful circuit is the dynamic logic, and I have drawn here the dynamic inverter. Right. So again, now let's talk about this particular inverter circuit, how it works. So I have a PMOS circuit with a width of 1. Right, and then an NMOS circuit with a width of 1. Input is applied only to the NMOS side, and then a clock is provided to the PMOS side. So the structure is very similar to that of again the Pseudo NMOS family, but the Pseudo NMOS family had always the PMOS to be on, so that means that the input or the gate of the PMOS was connected to the ground. Here it is connected to the clock signal. So what it means is whenever the clock is low, the PMOS, it ensures that the PMOS is on, and if the input is 0, so the NMOS will be off and the Y will be charged, or we can say that it will be pre-charged to VDD, right? It will be pre-charged to logic level high. And when phi is equal to goes to 1, that means when the PMOS is off, and then whatever is the input, whether it is 0 or 1, the Y will either stay at 1 if the input is 0, or if the input is 1, then the Y will completely get discharged to 0, right? So when phi is equal to 0, actually, that is called as the charging mode, or it is called as the pre-charging mode. And then when phi is equal to 1, that means the PMOS is off, that is called as the evaluation phase. Right. So when the PMOS is on, or when the phi is equal to 0, it is called as the pre-charge mode. And then when the PMOS is off, that means the phi is equal to 1. So phi is equal to 1, PMOS being off, that is called as the evaluation phase. So Y actually depends on the input. So during the evaluation phase, Y depends on the input, right? Based on the input, whether it is 0 or 1, the Y will be the complementary logic, right? And during the pre-charge phase, Y will always be 1. The input capacitance is always 1 here because the input is connected to the NMOS transistor, and then NMOS transistor width is nothing but 1, so the input capacitance is always 1C. Okay. So there are some advantages I have written here. So let's try to understand this. So before going into this particular understanding, let me try to summarize this. There is an pre-charge mode and then there is an evaluation mode. In the pre-charge mode, phi should be 0, and that is when the output will be connected to the VDD, or it will be charged to VDD. And in the evaluation phase, phi should be equal to 1, so that means the PMOS will be off, and then based on the input, whether it is 0 or 1, the Y will be retained to 1 or it will be discharged to 0, right? So there are some hiccups, I'll come to that in this particular circuit. So what should be the logical effort here? So the logical effort, in terms of, the V input, whether it is 0 or 1, if it is 0, it is retained to 1 logic, because in the previous phase, phi is equal to anyways be 0, and then the Y is charged to VDD, or the logic level high, right? The moment in the evaluation phase, that is when phi is equal to 0 or phi is equal to 1 in the evaluation phase, in the evaluation phase, and when it sees input to be 0, right, the Y will stay at 1, right? Only when the input is 0, Y will get discharged to 0, right? Only when V input is 1. So in this particular case, in this particular logic, we have to ensure that the input or whatever the evaluation happens, right? The evaluation, that is the output, is being evaluated based on the inputs. That happens only in the evaluation phase and not in the pre-charge mode, right? And in the evaluation phase, we are trying to find out what is the delay, right? So that means during our delay evaluation, what we need to find out is the logical effort and then the parasitics, right? The normalized parasitics. So my definition of the normalized the parasitics as well as the logical effort, right, will not be applicable for the rising output, right? The rising output, we will anyways have the pre-charge mode, which is anyways covered, and then when V input is equal to 0, it will stay at 1, right? So the logical effort and then the parasitic, normalized parasitics, is applicable only for when V input is equal to 1 in this case. So my output will actually get dropped to 0, right? So my logical effort is always, in a dynamic inverter, it will always be going down signal, and parasitic is also for the going down signal, because for the going up signal, the logical effort and parasitics is not at all applicable. Right. Now for the going down signal, the logical effort for the going down signal, it has a current of I here. So my benchmark inverter for the going down signal is nothing but 2:1 inverter. So my logical effort will be nothing but the input capacitance seen at this particular gate side. And remember that the PMOS and NMOS are not tied together. The PMOS sees a clock of 5, and the NMOS sees the input side, it is nothing but the input V in. So my logical effort sees a capacitance of, the input capacitance of 1 here, and that will come in the numerator side divided by the benchmark inverters 2:1. So it sees a capacitance, input capacitance of 3. So the logical effort is nothing but 1/3. Similarly, the parasitics, for the parasitics, the benchmark inverter is again 2:1. At the output side here, I'll see a capacitance, total capacitance of 1 and 1. So there is a capacitance of 2C here. And the benchmark inverter is going to give a capacitance of 3. So the parasitic will be 2/3 for the going down, right? So there is no values defined for the going up signal. So that means that there is no values for stated for the logical effort for the going up and then the parasitics for going up. Okay, so let me quickly go through this particular 3 statements. The input capacitance is 1C here, that is correct. And it turns out to be the lowest among all the circuit families and hence the fastest, right? If I compare the regular inverter, it has a 2:1. So the input capacitance is actually 3C. Pseudo NMOS family inverter, if I look into it, it is 2/3 and 4/3. And then if I choose that 4/3 on the input side, it is actually the capacitance is 4/3, which is greater than 1C, right? So hence in this case, it turns out to be, the overall input capacitance is low, and thereby it becomes the fastest. And no contention during the output falling and rising, assuming that the input is not 1 during the pre-charge mode, right? Input is not 1 during the pre-charge mode, that is during when phi is equal to 0. I'm going to eliminate this and then say that phi is equal to 0 here. So that means that the PMOS is on. And if input is not 1, the reason is if input is 1, if input is 1, I will have NMOS and PMOS both to be on. And thereby, there will be a current here and then there will be a current here. So the VDD will supply the current to the ground. So assuming that in the pre-charge mode, when phi is equal to 0, V input is not equal to 1, right? V input could be, we will ensure that the V input stays at 0. And then only in the evaluation phase, when it goes to the evaluation phase, that is when phi is equal to 1, that is when the input is applied, I will have no contention during the output falling or rising. Okay. The foot transistor is included to avoid the problem of switching the input during the pre-charge mode. So what I said was when phi is equal to 0, I don't want the input to be 1. So in that case, if input doesn't stay to be 0 and if it switches to 1, then I can do something to avoid the contention. So that is what we will see in this third statement in the next slide. Right, hope this is clear up till so far. Right, the foot transistor. Right, so we have added one more transistor, and if I add one more transistors on the pull downside to get a switching resistance of R, which is same as that of 2:1, the regular inverter, I'll have to make the width of 2 here and then 2 here. In the previous case, the width was 1 and 1 here, but now it has become 2 because there are 2 stacked transistors. The input here is phi here to the foot transistor. Foot transistor, the transistor which is closer to the ground drain, that is called as a foot transistor. These two transistors work similarly the way we had seen previously. There is an additional foot transistor, that's it, and then the input of to this particular foot transistor is nothing but the clock which is provided to this PMOS transistor. So again, the everything remains the same. When phi is equal to 0, this is called as a pre-charge mode. When phi is equal to 0, this foot transistor will be off, this PMOS will be on, and then the output will be charged to VDD or logic level high. When phi is equal to 1, evaluation mode comes in. The foot transistor will be on. When phi is equal to 1, foot transistor will be on. This will be off, right? So the pre-charge is done. We are now into the evaluation phase, and based on the input, it will either stay at, VDD, or it will be discharged to 0, right? So if V input is 0, there is no complete discharge path to the ground. Right, and thereby Y will be retained to logic level high. Whenever the V input is 1, the Y will have a discharge path coming from the N1 transistor as well as the foot transistor and to the ground. So that's what I have written, Y is equal to 0 and Y is equal to 1. So the logical effort for the going down signal now will be slightly higher because the width is 2 here. So the input capacitance seen at the input side will be 2. And my benchmark inverter is anyways 2:1 inverter, so I will have an input capacitance of 3. So the logical effort for going down signal is 2/3. The parasitics now will also increase because now I see the parasitic capacitance at the output node is nothing but 2 plus 1, so it will be 3C. So I will have a parasitic capacitance of 3 here divided by the 3 which is coming from our 2:1 inverter. So the parasitic value will be nothing but 1.